Okay, then next topic is humidity chart or psychrometric chart, we can call this one. So what is this humidity chart? So what is this humidity chart? So it is a very convenient diagram to represent all the values which are there for the gas and liquid system. So it is a very convenient diagram showing the properties of a permanent gas, that is nothing but air, and condensable vapor, that is a water vapor. A chart for a mixture of air and water at 1 atma is often referred as humidity chart, in which temperatures are plotted on abscissa, that is nothing but x-axis, and the ordinate will be the humidity. So this one, or y-axis, will be humidity. So any point on this chart will represent a definite mixture of air and water. So for the air and water system, this is the humidity chart. For the same any type of liquid and gas system, we can draw this diagram. But usually in the humidification chart and weather reporting stations, or in many material reporting station, this will be the chart which is for air and water system, in which the temperature will be there on the abscissa, that is called an x-axis, and pressure this humidity will be reported in the y-axis, that is ordinate system. Then the left of this chart will be the volume, and top of this chart will be the humid heat CS value, this one. So these are the four different coordinates which are there inside this single chart. So it is a very convenient diagram, therefore, to represent all the properties which are required for the permanent gas and the water vapor which is there at that particular temperature. So the whatever the curved lines which are there here, so this one 100%, 90%, 80%, 70%, 60%, all these lines are nothing but a humidity. So that this 100% line is nothing but the saturation humidity. So humidity of saturated air as a function of temperature. So humidity of a saturated air at 100 temperature. So 100% is the maximum capacity that air has to be attained, that air has to absorb the water content. So any point above this to the left side, okay, to the left side, any point above this saturated line, that is 100% line, is nothing but a mixture of saturated air and a liquid. And the region is also very important to check the formation of your fog. Okay, whether fog is forming or not, to know that one, the lines which are there above this one, so above this section, will give that particular thing in the weather reporting station. And any point below this one, okay, below this 100% line, so that is called as a undersaturated line, undersaturated air. Why? Because below 100%, that is 90%, 80%, 70%, all these are nothing but still air is getting saturated. So a point on the temperature axis which will be represented as a dry air. Okay, this one. So below this 10%, all this will be coming as a dry air. So after this one, slowly the water vapor will be added and it will be coming until the saturation. So the 100% line below this line, so everything will be called as a undersaturated line. Okay, this is the undersaturated line. This is after saturation. This will be very important in order to calculate the humidification, that fog formation. Then the linear interpolation between the saturation line, this 100% line, and the temperature axis, this one, temperature axis, can be used to locate the line to get a constant percentage humidity. And the slanting line, this one, so the slanting line which is running downward, to the rightwards of this saturated line, are called adiabatic cooling lines. So these are called adiabatic cooling lines. So 135, 140 degrees, 135 degrees, 130 degrees, 125 degrees, okay, 120, 115, 110, 105. All these slanting lines are called as a adiabatic saturation line, whose slope will be minus Cs by lambda s. Now we have whatever the derivation we have derived. So that is the slope. Minus Cs by lambda s is the slope of that line. So each line drawn for a given set of constant value of adiabatic saturation temperature. For each Ts value, there will be one saturation adiabatic cooling lines for that one. So for a given value of Ts, both Hs and lambda s are obviously fixed, and the line of H versus T. So H versus T, this one, H versus T can be a plot which is assigning the values of H and also converting the corresponding values in the T value. So from this equation, So whatever this Cs by lambda S equation is there, no, is equal to H minus Hs by T minus Ts. So using that only, we will be drawing this adiabatic saturation line. In that one, Cs we already know. Cs is equal to Cpb plus Cpa into H. So that are the lines. Then here in the right side or left side, there is a volumes which can be read on this scale. So volume. So there are two volumes. One is a saturated volume. Another one is a specific volume of a dry air. So saturated volume of a dry air, a saturated volume of your air versus the temperature is this curve. Okay, this curve. And the specific volume of a dry air versus the temperature is this line, which will be representing this line. Then the interpolation between a linear interpolation between the two lines based on this percentage humidity, whatever the percentage humidity is there, so gives the humid volume of a saturated air, VH. Okay. After interpolating these two lines, saturated volume and the specific volume of a dry gas line. So after linearly interpolating that one, we can get a value for the specific percentage humidity. What is the value of humid volume, VH, we can get. Also the relationship between this humid heat and also the humidity. So humid heat and the humidity versus this one. CS versus the humidity. This will be represented by this line. So all these quantities, there are 7 interdependent quantities will be there. So based on this 7 interdependent quantities, if you know any of the 2 quantities, you can calculate the remaining 5 quantities very easily using this humidity chart or a psychrometric chart, we can call this one. So this humidity chart or the psychrometric chart will be usually prepared for number of gases and vapor systems, so that it is very convenient. We don't have to conduct every time experiments. Okay, by referring this chart, what is the value of Ts, what is the value of Cs, what is the value of VH, what is the value of humidity, what is the value of percentage humidity. So like that we can calculate if you know any of the 2 quantities. So there are many 7 quantities, like a wet bulb temperature, we have 1 quantity, dry bulb temperature, relative humidity, absolute humidity, specific volume, enthalpy, dew point. Okay, we need not to know all this one, all the 7 quantities for every time, every system at every temperature. So we have a humidity charts like this. If you know any of the 2 quantities, the remaining 5 quantities from the 7 quantities will be easily we can estimate using the humidity chart. So that is the humidity chart where its beauty will come. So if you know any of the 2 parameters, the remaining parameters can be calculated very, very easily. So I will try to explain once again this after drawing here. So this is a psychrometric chart, or we can call as a humidity chart. Psychrometric chart or humidity chart. So how this will looks like, the psychrometric chart or the humidity chart. So this is called abscissa. X-axis is called abscissa, and y-axis will be called as a ordinate. Ordinate. So x-axis will be your temperature, usually given in degree Fahrenheit, and y-axis will be your humidity. So usually in the FPS system, that is lb pound of water vapor per pound of your gas or air, we can say. Usually for the air water system, these are the very convenient diagrams. Then here it will be on the left side, it will be volume. So in the FPS system, it is feet cube per lb air. And on the top of this one will be the CS, that is nothing but humid heat values. Humid heat CS values will be there. Usually this humidity will be expressed in FPS units as BTU per LB degree Fahrenheit. So these are the overall axes. So first is the line like this. So 0% of humidity means it is a dry air. So dry air means zero moisture or zero humidity is called 0%. And that air, what we call air temperature, at that particular temperature, what is the humidity of the air? H versus this T. Then after that one, so slowly you will be in the adiabatic saturator. What happens? The air is getting inside and air is getting outside. So in between them, we are spraying some water like this. So whenever you are spraying, the inside air temperature will be increasing. So temperature of air will be increasing. So after air is increasing, how much amount of water vapor we are adding to that one? That will be representing like this one. This curves. So that is some 10% humidity. Then after that one, H versus T will be once again drawn like this. So this represented 20% humidity. Then this will be representing 30% humidity. So like this, the n number of lines will be there. So finally, you will get 100% humidity. That is a saturation humidity. Saturation humidity. So already air is completely reached its capacity. That is called 100% line. So that is Hs is equal to 100% saturation line. So after reaching this line, okay, after reaching this line, what happens? The slanting lines, okay, the slanting lines which are there here. So like this. So this is called adiabatic saturation line, adiabatic cooling lines. So this adiabatic cooling lines can be drawn using this equation, that is Cs by lambda s is equal to Hs minus H minus Ts. Okay, this is H minus Hs, H minus Hs by T minus Ts. Using this one, we can draw. So minus, so this line will have a slope of minus Cs by lambda s. So using that only, we can draw that one. So that is called adiabatic cooling lines. So this is at, for example, there is 140 degrees and at 135 degrees, 135 degrees. So then this then 135, then 120, 125, like this n number of adiabatic saturation lines will be there. And there will be some specific volume versus your dry air, volume of your dry air versus temperature. That is specific volume versus temperature. And next is the line which is your saturated volume versus temperature. So this is saturated volume versus temperature. And then the last line will be there, that is humid heat versus your humidity. This is like this. This is Cs value versus Cs versus temperature. So these are the lines, various lines which will be there in the humidity chart. So this will be drawing based on the various conditions. So like adiabatic cooling lines can be drawn using this uh, particular equation, that is, okay, this equation is wrong, I think. So this is Cs by lambda s is equal to H minus Hs by Ts minus T. That is minus Cs by lambda is equal to Cpb plus Cpa into H by lambda s minus. So this minus Cs by lambda is nothing but your slope of this particular line. For each set of temperature, there will be one adiabatic cooling line will be there. That's why for 140 this one, 135 this one, 130 this one, 120 this one, 125 that one, like this. Then there is a volume. Okay, there is a specific volume versus temperature and saturated volume versus temperature. After interpolating these two for the particular temperature, we can obtain the value of VH. Okay, that is humid volume using the following equation, that is 359 T by 492 into 1 by MB plus H by MA. This can be obtained using a linear interpolation between saturated volume versus temperature and specific volume versus temperature lines. We can obtain the various values. Okay, is it clear? Psychrometric chart or humidification chart or humidity chart?
Yes, sir.
Okay, so this is also very important. You have to go through this one. So for example, this humidity chart you have to draw in the examination whenever they are asking, explain in detail about humidity chart. So humidity chart is nothing but a convenient diagram showing the properties of a permanent gas, which is nothing but air, and the condensable vapor, which is nothing but water vapor. So a chart for mixture of air and water at 1 atma is often referred as humidity chart, in which temperature are plotted as a abscissa or x-axis, and this humidity on the ordinate, that is called as a y-axis. Any point on the chart represents a definite mixture of air and water. So the curved lines marked 100%. So this line, so marked 100%, gives the humidity of saturated air as a function of air temperature. By using the vapor pressure of water, the coordinates of points on the lines are found from Hs is equal to Ma into vapor pressure divided by Mb into total pressure minus vapor pressure. Using this equation, we can obtain this Hs versus temperature. So this 100% line. Then any point above to the left of the saturation line represents a mixture of saturated air and a liquid. So this region, so above this one, so this left region, they are saying. So this region is important only in checking fog formation. And any point below the saturation line represents undersaturated air, and a point on the temperature axis represents dry air. So this region, so this right region compared to this 100% region, all these lines shows the air is undersaturated air. Then the curved lines between the saturated line and a temperature axis marked in even percentage represents mixture of air and water at definite percentage humidity. So as shown in this equation, the percentage humidity can be calculated. That is nothing but a ratio of H by Hs. So absolute humidity divided by saturation humidity, that is 100% line and this line. Okay, so these two lines into 100. So that is always equal to relative humidity multiplied by total pressure minus vapor pressure divided by total pressure minus partial pressure. Using this equation, we can find out all these lines. Then the linear interpolation between the saturation line and the temperature axis can be used to locate the line of constant percentage humidity. Then the slanting line running down to the right of the saturated line are called adiabatic cooling lines. That is this line, the slanting lines which are running back, okay, to the right of this adiabatic saturation is called this adiabatic cooling lines. That point is that one. They are plotted using the equation H minus Hs by T minus Ts is equal to minus Cs by lambda S is equal to minus Cpb plus Cpa into H divided by lambda S. Using this equation, this slanting lines can be drawn for 140 degrees, 135, 130, 125, 125, 20, 115, 110 like this. We can draw for n number of lines like that. So in this one, H is the humidity, H is the saturation humidity, T is the temperature, Ts is the adiabatic saturation temperature, C is the humid heat, and lambda S is the latent heat of vaporization at saturated condition, Ts. Then Cpb is the specific heat of the your particular gas, and Cpa is the specific heat of your water vapor, H is the humidity, and lambda is the latent heat of vaporization at a saturation condition. Then what is the adiabatic cooling line? So the adiabatic cooling line represents the conditions of gas of constant wet bulb temperature and a constant adiabatic saturation temperature. Then the change in the condition of a gas as it is humidified with water vapor is therefore represented by adiabatic cooling line. And the intermediate conditions of the gas during the process are readily obtained. So this is particularly useful because only partial humidification is normally obtained in practice. So absolute and 100% saturation is not possible. Okay, in the actual practices, there may be many lagging behind the equipments. There may not be feasible or economical to do all the saturation process. That's why. So absolute complete saturation is not possible. So undersaturated air only will be partial humidification only will be taking place in the practice. Then each adiabatic cooling line represents the composition of all gases whose adiabatic saturation temperature is given by its point of intersection with the 100% humidity curve. Means this one. So 100% humidity curve. For the air and water system, the adiabatic cooling lines represents condition of constant wet bulb temperature as well as previously mentioned enabling the change in composition of a gas to be followed and it's humidified by contact with air at adiabatic saturation temperature of the gas. Whatever the process we have seen, adiabatic saturation process, using that process only we can estimate what is the adiabatic saturation temperature, and from that one we can draw this adiabatic cooling lines. Then each drawn for the given constant value of adiabatic saturation temperature. For each Ts value, we will be having one adiabatic cooling line we will have. So for a given value of Ts, that is adiabatic saturation temperature, both Hs and lambda s are fixed, and the line H versus V, H versus T can be plotted by assigning the values of H and calculating the corresponding T values using these lines. Okay, using this line. For each H value, this will be function of temperature. Then from the equations, in the slope of the adiabatic cooling line when plotted on rectangular coordinates or minus Cs by lambda s is the slope of the particular line. We know that Cs is nothing but humid heat, which is nothing but the sum of the specific heats of gas plus specific heats of your water vapor. So the slope depends on humidity itself. The Cs is one point in the slope that is dependent on humidity. So after knowing humidity only, we can draw this adiabatic cooling lines. Then the lines are shown in the figure for a specific volume of the dry air and the saturated volume. Both lines are plots of volume versus temperature. So these lines. So this specific volume, saturated volume versus temperature. So this is specific volume versus temperature. These two lines are nothing but volume versus temperature plots. Okay, that one. So volumes are read on the scale at the left coordinate of the points on these lines are calculated using equation. So this equation can be used to calculate what is the specific humid volume. Okay, humid volume of that particular mixture. Then the linear interpolation between the two lines based in percentage humidity gives the humid volume of saturated air. So interpolation between these two lines, we can estimate the humid volume easily. So then also the relationship between humid heat Cs and versus humidity is shown as a line on figure is a plot of equation Cs, and Cs is equal to Cpb plus Cpa into H. That is the top of the chart, this one. So this line Cs versus humidity. So Cs is this one and humidity is this coordinate. So both the functions we can draw this line. That is called Cs versus humidity line. Using this equation you can draw that one. So this slope depends on humidity itself. It is dependent. Okay, this one. The scale of Cs is on the top of the chart. There is Cs which is there in the top of the chart. That is humid heat. So that is about the humidification chart. I hope it is clear.
Yes, sir.
Yes, sir.